Module 1, Relational Summary Lecture GSE1, Southern Oscillations and Ripple Effects. In Neville Shute's chilling Cold War novel, On the Beach, which appeared in 1957 and was made into a feature film 2 years later with Hollywood stars Gregory Peck, Ava Gardner, Fred Astaire, and Anthony Perkins, the last survivors of the human race find themselves in the land down under, waiting to see if the fallout from a global nuclear war will reach them. As Wiki's plot synopsis tells it, quote, in early 1964, in the months following World War III, the conflict has devastated the entirety of the northern hemisphere, killing all humans after polluting the atmosphere with nuclear fallout. Air currents are slowly carrying the fallout south. The only areas still habitable are in the far reaches of the southern hemisphere, end quote. The hope is that being far away from civilization, far in the southeast quadrant of our planet, separated by the vastness of the Pacific Ocean, can protect us from the negative effects of civilization. But as the haunting last scene of the movie shows, as our heroes succumb to the inevitable and invisible fallout, ultimately we all exist in a single sphere with interconnected air and water currents and carbon, nitrogen, phosphorus, and other nutrient and material cycles. What goes around comes around, literally. It's still hard for most people who don't study science or geography to accept that. You can call it karma if you like, but it's really just the simple consequence of being in a biosphere where nothing gets in but sunlight and the occasional meteor or asteroid, and nothing leaves except a few space probes and heat, when it's not prevented by infrared radiation trapping gases. The interconnectedness and fragility of it all were truly driven home when NASA first released its blue marble photo in 1972. But people have been feeling the impact since the famous Earthrise photo taken Christmas Eve of 1968, as the Apollo 8 spacecraft rounded the dark side of the moon, and even longer. The first Earth from space image was actually shot by rocket scientists on October 24th of 1946. One thing that all of those photographs of the Earth from space and so many others revealed was that we really don't live on a planet Earth at all, but on a planet ocean. And nowhere is this more evident than in the southern hemisphere. The south, you see, is mostly ocean, and that makes a whole hell of a lot of difference when it comes to climate. First, there aren't that many cities or that many people adding greenhouse gases to the problems there. The largest cities are Jakarta, 32 million people, Sao Paulo, 22 million, Buenos Aires, 16 million, Rio de Janeiro, 12 million, Kinshasa, 11 million, Lima, 10 million, Johannesburg, 10 million, Santiago, 7 million, and Sydney, 5 million. Even the most populous of the southern nations, Indonesia, lies mostly in the northern hemisphere. Fortunately, most of the remaining wildlands and their carbon-sequestering ecologies do lie in the south. But water is the most salient feature of the south, and water absorbs a lot of CO2 and a lot of heat. Water is a heat sink because of what is called its enthalpy. Wiki's entry on ocean heat content tells us, quote, in oceanography and climatology, ocean heat content, OHC, is a term for the energy absorbed by the ocean, which is stored as internal energy or enthalpy. Changes in the ocean heat content play an important role in sea level rise because of thermal expansion. Ocean warming accounts for 90% of the energy accumulation from global warming between 1971 and 2010. And about 1/3 of that extra heat has been estimated to propagate to a depth below 700 meters. Beyond the direct impact of thermal expansion, ocean warming contributes to increased rates of ice melt of glaciers and fjords of Greenland and ice sheets in Antarctica. Warmer oceans are also responsible for coral bleaching, end quote. Now think about it. The Southern Ocean is the world's most massive heat sink, and it picks up most of that heat because it has a vast surface area exposed to the sun, unlike the thermal mass of land, which experiences relatively rapid adiabatic heating and cooling. The ocean stores the heat for much longer and releases the heat much more slowly. In addition, water vapor itself is a powerful heat-trapping gas. So what happens when you cover the planet with other greenhouse gases that trap the heat? The net effect is to keep the warming going for much, much longer. And any change to the ocean heat content exchange in the Southern Ocean has profound effects on the entire planet. Says NASA, quote, the most important mechanism is latent heat release or evaporation. Over the ocean, latent heat is the engine that drives atmospheric circulation. As the sun beats down and the ocean warms, water from the upper layer of the ocean evaporates. The conversion of liquid to vapor requires a lot of energy, so evaporation cools the top layer. Think of how sweat evaporating from your skin cools your body. Trade winds then carry the vapor to the area where the north and south trade winds converge, called the Intertropical Convergence Zone, or ITCZ. There, the moist air rises and cools. The water vapor condenses on tiny particles suspended in the air called nuclei, forming clouds. This condensation releases energy, heating the surrounding air. The warmed air then rises even higher, drawing up more moisture from the ocean. More vapor then condenses higher in the atmosphere and releases more heat, causing the air to rise further, and so on. The result is towering clouds that dump up to 5 meters of rain per year over some parts of the tropical ocean. There's a diagram of the fast carbon cycle that shows the movement of carbon between land, atmosphere, and oceans. Yellow numbers are natural fluxes and red are human contributions in gigatons of carbon per year. White numbers indicate stored carbon. The diagram's adapted from the US DOE Biological Environmental Research Information System. Now, carbon flows between each reservoir in an exchange called the carbon cycle, which has slow and fast components. Any change in the cycle that shifts carbon out of one reservoir puts more carbon in other reservoirs. And changes that put carbon gases into the atmosphere result in warmer temperatures on Earth. This same process fuels hurricanes. At the centers of these storms, moist air rising from the warm ocean heats up as the water vapor condenses. And then, since warm air is less dense, the atmospheric pressure drops. More moist air then rushes in off the ocean due to the pressure gradient, rotating counterclockwise due to the Coriolis effect. This air rises up and condensation releases more heat, intensifying the storm and further lowering the pressure. Hurricanes generally don't form close to the equator because the Coriolis effect is weak. Now, taking a global perspective is important. What happens in oceans on the other side of the globe certainly affects us wherever we are. As National Geographic pointed out in a March 2019 article, quote, "Since warm ocean waters are essential to form and maintain a hurricane, scientists wondered if there was a connection between warmer ocean temperatures and an increase in hurricane frequency and strength. Scientists have been examining the effect of climate change on sea surface temperatures around the globe, using records from as far back as 1880. The data shows a significant surge in global sea surface temperatures, and researchers suspected that climate change was playing a part in these warmer waters, but they needed to find proof." Now, Ethan Gutman, a project scientist at the National Center for Atmospheric Research, found a way to show how climate change would affect hurricanes. Gutman ran a computerized simulation of 22 named hurricanes that occurred between 2001 to 2013. In the simulation, he changed the temperature, the humidity, the wind speed, and direction to mimic the conditions expected in the future as a result of climate change. How did the hurricanes respond to climate change? The hurricanes all had more rain and, on average, stronger wind speeds, but each hurricane reacted differently to climate change. While some scientists believe there is enough evidence to say that climate change caused by human activities is the reason for the increase in the number and strength of recent hurricane seasons, other researchers are still unsure that climate change is the only cause. That's important. Since hurricanes form without any help from humans, scientists know that there could be other things in nature influencing their formation and strength that have nothing to do with climate change. One example is an El Nino or La Nina event. El Nino and La Nina events cause unusual warming or cooling of the ocean waters near the equator, affecting weather patterns around the world, end quote. Okay, that's all fine and good, but by October of 2019, new data was published in an article by the Yale School of the Environment saying, quote, "Climate change is increasing the frequency of extreme El Nino events, leading to intensifying droughts, worsening floods, and shifting hurricane patterns, according to a new study published in the Proceedings of the National Academy of Sciences," end quote. So it is a bit disingenuous to separate, quote, natural phenomena that create hurricanes, floods, and fires, and climate change as if there's no relationship. And of course, believing that anything is the only cause in a complex system is foolhardy. No scientist would ever say anything is the only cause. It would be like saying, quote, "cigarette smoking is the only cause of lung cancer." No. Obviously, there are many compounding and confounding causes for the troubles we face. But prudence suggests that we always start where we know we can have an effect. For example, you may inhale carcinogens every day driving to work, and you may not be able to avoid it. But you should still have your basement checked for radon leaks, and for God's sake, give up smoking, right? The same would be true of anthropogenic causes of climate change. We can't control planetary patterns like El Nino events, but still, we can stop adding things to the atmosphere that can exacerbate them. And now we have studies that are making the link clearer. Quote, the study, led by scientists in China and the United States, examined data from 33 El Niños dating back to 1901. It found that since the 1970s, El Nino, a natural periodic warming in the Pacific Ocean that can change weather patterns globally, have been forming farther to the west in the Pacific Ocean where temperatures are warmer. Strong El Niños can cause severe drought in dry climates such as Australia and India, intense flooding in wetter climates such as the Pacific Northwest and Peru, and causes more hurricanes to form in the Pacific and fewer in the Atlantic. Before 1978, 12 of 14 El Niños formed east of the international date line, the study found. Since 1978, all 11 have formed in the central or western Pacific Ocean, a shift of hundreds of miles, the Associated Press reported. There have been 3 super El Niños since the shift, in 1982, 1997, and 2015, that broke new average temperature records and triggered catastrophic natural disasters. The 1997-1998 El Nino, for example, caused thousands of deaths from severe heat, flooding, drought, and coastal storms, and generated as much as $96 billion in damage, according to the United Nations. If global temperatures keep rising, El Niños could continue to intensify, with major impacts on societies around the world. Quote, if the observed background changes continue under future anthropogenic forcing, that is human-induced global warming, more frequent extreme El Nino events will induce profound socioeconomic consequences, end quote, the scientists wrote. And we shouldn't be surprised. Once again, we're talking about an interconnected system, and the literal and figurative ripple effects of changes in one area are felt planet-wide. As the Bureau of Meteorology in Australia states, quote, El Nino events are associated with a warming of the central and eastern tropical Pacific, while La Nina events are the reverse, with a sustained cooling of these same areas. These changes in the Pacific Ocean and its overlying atmosphere occur in a cycle known as the El Nino Southern Oscillation, or ENSO, end quote. Having lived through periods in California in the 90s when wildfires were attributed to El Nino events far away, I got sensitized to the butterfly effect. The idea that small perturbations in one area can lead to major consequences in another, even on opposite sides of the biosphere. I'm sensitive to any exacerbation of the phenomenon's reach, especially during these years when wildfires happen with greater and greater frequency. So when we look at the current politics surrounding climate change, and the claims made by the former president and vice president that the fires were actually due to mismanagement and a lack of rakes, can we all forget for a moment that they are occurring on federal lands under that administration's jurisdiction for the past 4 years? And that hurricanes, the claim that hurricanes aren't increasing in frequency, we see how a misunderstanding of the science of southern oscillations and a misunderstanding of science in general has been exploited to pass the buck when it comes to ensuring our health and safety. To be clear, no serious scientist says that anthropogenic climate change alone is causing anything. No true scientist says that climate change isn't natural. But we agree that humans are part of nature. So that's a moot point. And when we say hurricanes are getting worse, it doesn't matter if the raw number of hurricanes is staying constant over the century or changing, because it's the intensity and size and characteristics and damage potential of hurricanes that is at issue. There could even be fewer hurricanes in the future. We would still have to do something about the role that anthropogenic greenhouse gases play in their exacerbation if they are more life-threatening and do more damage than a lot of weaker ones in the past. The previous anti-science administration, beholden to fossil fuel lobby interests, was hell-bent on deflection and sowing confusion. And ultimately, they were using science against itself. Whenever they said that scientists are still uncertain or scientists still don't know, This means something completely different to when a layperson expresses doubt. We don't need untrained climate skeptics in the dialogue, if they even know how to conduct a respective dialogue, because all true scientists are climate skeptics. In fact, all true scientists are everything skeptics. Science is all about skepticism. The standard of proof in science is so much higher than in any other field, including jurisprudence, that you should never have any scientist claiming to have found airtight proof for any hypothesis or theory. When Natural Resources Agency Secretary Wade Crowfoot urged the previous president, to, quote, recognize the changing climate and what it means to our forests, end quote, during the fires in California, Trump responded,
"Start getting cooler. You just watch."
According to AP Wire, Crowfoot politely pushed back that he wished the science agreed with the president, and Trump countered, "I don't think science knows, actually." But this is a total canard. As Wired magazine correctly put it, quote, science isn't about the truth, it's about building models. Scientists are obligated to say they don't definitively know the answers to anything. To say anything with 100% confidence is impossible in a field whose power comes from managing uncertainty by staying within confidence intervals given through statistical modeling. But let's leave further discussion of this for the politics section of this unit. Ecologically, the science is clear. For all of the uncertainty in the models, the net effect is more extreme events. Summary, 97% of working climate scientists, 31,000, say the temperature is rising and human activity is a significant contributing factor. Significant. Says the AP, quote, Trump's suggestion that the planet was going to start unexpectedly cooling is at odds with reality, experts say. Maybe there is a parallel universe where a pot on the stove with the burner turned to high starts getting colder, they said, but that's not our universe. This from Stanford University climate scientist Chris Field. And so, paradoxically, while it is good for our common future that there aren't many inhabited land masses in the southern hemisphere to add to the greenhouse gas emission cabal, one of the problems with the ecological south that we must plan for is precisely that the huge ocean volumes are so good at storing and holding carbon and heat for lengthy periods of time. The problem comes when the sink is saturated. As CO2 builds up, it acidifies the ocean, causing coral bleaching, killing the coral and plankton, and dissolving shells that would otherwise permanently sequester the carbon. And this leads to the release of more CO2 into the water, increasing the acidity. Then the heat drives a lot of the CO2 back out into the atmosphere because warm water can't hold as much CO2 as cold water. But it doesn't improve the pH of the water because the water is oversaturated to begin with. So what we see happening is a runaway positive feedback loop, which the laws of physics in this universe tell us can only get worse, and with a heat and carbon sink that big, can keep getting worse for decades, if not centuries to come, even after we have completely ceased emitting the greenhouse gases responsible for most of this. A good article in The Conversation explains how this works and should be a good conversation starter for you. They say, quote, what would happen to the climate if we were to stop emitting carbon dioxide today, right now? Would we return to the climate of our elders? The simple answer is no. Once we release the carbon dioxide stored in the fossil fuels we burn, it accumulates in and moves among the atmosphere, the oceans, the land and the plants, and the animals of the biosphere. The released carbon dioxide will remain in the atmosphere for thousands of years. Only after many millennia will it return to rocks, for example, through the formation of calcium carbonate, limestone, as marine organisms' shells settle to the bottom of the ocean. But on time spans relevant to humans, once released, the carbon dioxide is in our environment essentially forever. It does not go away unless we ourselves remove it. In order to stop the accumulation of heat, we'd have to eliminate not just carbon dioxide emissions, but all greenhouse gases such as methane and nitrous oxide. We'd also need to reverse deforestation and other land uses that affect the Earth's energy balance, the difference between incoming energy from the sun and what's returned to space. We would have to radically change our agriculture. If we did this, it would eliminate additional planetary warming and limit the rise of air temperature. such a cessation of warming is not possible. So if we stop emitting carbon dioxide from burning fossil fuels today, it's not the end of the story for global warming. There's a delay in air temperature increase as the atmosphere catches up with all the heat that the Earth has accumulated. After maybe 40 more years, scientists hypothesize the climate will stabilize at a temperature higher than what was normal for previous generations. This decades-long lag between cause and effect is due to the long time it takes to heat the ocean's huge mass. The energy that is held in the Earth by increased carbon dioxide does more than heat the air. It melts ice, it heats the ocean. Compared to air, it's harder to raise the temperature of water. It takes time, decades. However, once the ocean temperature is elevated, it will release heat back to the air and be measured as surface heating. Scientists run thought experiments to help think through the complex processes of emissions reductions and limits to warming. One experiment held forcing, or the effect of greenhouse gases on the Earth's energy balance, to the year 2000 levels, which implies a very low rate of continued emissions. And it found as the ocean's heating catches up with the atmosphere, the Earth's temperature would rise about another 0.6 degrees Celsius. Scientists refer to this as committed warming. Ice, also responding to increased heat in the ocean, will continue to melt. There's already convincing evidence that significant glaciers in the West Antarctic ice sheet are lost. Ice, water, and air, the extra heat held on the Earth by carbon dioxide affects them all. That which is melted will stay melted, and more will melt. Ecosystems are altered by natural and human-made occurrences. As they recover, it will be in a different climate from that in which they evolved. The climate in which they recover will not be stable. It will be continuing to warm. There will be no new normal, only more change." End quote. Wow. Ultimately, however, I have faith that we sapient humans should be able to harness those changes to mitigate those changes. I mean, look at good drawdown solutions that we should be able to pull from our drawdown solutions cloud, like number 29, wave and tidal power, estimated to reduce CO2 by 9.2 gigatons at a net cost of $411.8 billion. But the savings so far appear to be negative financially until the infrastructure is well established, and that's why it isn't seeing a lot of implementation yet. But there have been some successful installations in the far north, particularly by a company called Wave Energy Scotland, and there's been development for decades in the South Pacific, like in Oahu, Hawaii. And recently, Bombora Wave Power in Western Australia has successfully deployed this clean source of electricity since 2015. But it isn't anything new. As a quick wiki shows us, quote, the first known patent to use energy from ocean waves dates back to 1799 and was filed in Paris by Girard and his son. An early application of wave power was a device constructed around 1910 by Beauchot-Prassaic to light and power his house at Royan near Bordeaux in France. It appears that this was the first oscillating water column type of wave energy device. From 1855 to 1973, there were already 340 patents filed in the UK alone, end quote. What is new and changing is the energy found in the waves. The more the globe warms up, the more the hydrosphere and atmosphere must shed that kinetic energy to reach equilibrium. And so, as we all know, the frequency, size, and intensity of storms and their ripple effects is increasing. But ironically, that means more energy to use to offset that generated by fossil fuels. And if we build out the infrastructure, regardless of the cost, we can end up obviating the need for fossil energy altogether. And then, when the carbon is drawn down, continue to exploit the natural background force of the ever-present waves and tides and winds. In fact, turbines that capture the energy of the wind are so important to this effort that wind turbines are ranked number 2 of the 100 drawdown solutions. Onshore wind energy is estimated to be able to offset 84.6 gigatons of CO2 at a cost of $1.2 trillion and a nice savings of $7 trillion. Offshore wind, wind at sea, is estimated to be able to reduce CO2 by 14 gigatons at a cost of $572 billion with a net savings of $274 billion. Not as extreme as savings perhaps, but consider this. Quote, offshore wind farms could tame hurricanes before they reach land, said the Stanford report back in February 26, 2014. Computer simulations by Professors Mark Jacobson have shown that offshore wind farms with thousands of wind turbines could have sapped the power of 3 real-life hurricanes, significantly decreasing their winds and accompanying storm surge, and possibly preventing billions of dollars in damages, end quote. Now, those are billions not calculated in the net savings. And Smithsonian Magazine revisited this concept in 2018, noting that, quote, in 2014, a group of researchers, including Christina Archer, a civil and environmental engineer from the University of Delaware, showed how using an army of wind turbines to extract kinetic energy from the air could potentially pacify hurricanes. The team calculated that a massive array of 78,000 turbines could reduce coastal storm surges, such as the one Hurricane Katrina shoved onto New Orleans in 2005, by up to 79%, end quote. Follow-up work 4 years later suggested that, quote, with enough turbines, the rainfall from Hurricane Harvey could have been reduced by 20%, end quote. So as we calculate the costs and savings, we really need to include all the negative externalities and positive externalities as ever. In these cases, it looks like the stronger our storms and waves and winds become, the more chance we have to use that unprecedented bad energy for unprecedented good, if only we can get the infrastructure in place in time.